So good morning, everyone. Last class, we discussed few aspects of control systems. Just to refresh what we discussed in the last class, this automatic control engineering or control systems engineering is a discipline in itself. What we discussed yesterday was through knowledge of control systems or through knowledge of modeling and simulation of physical systems, how we can plan our new product design and how we can predict the performance of a newly designed product. This is a wonderful tool, one should know, and that's why it has got a multidisciplinary flavor as such. It's not that only electronics engineers study this. It's not that electrical engineers and mechanical engineers can study this. Every branch, every discipline of engineering or sciences can study the principles of control system analysis. Even the weather prediction systems, geographical systems, weather demographic systems, in many applications. These principles of control systems analysis are used for predicting the performance. As I said, the population prediction is done by using principles of mathematical modeling, which are based on control system analysis as such. Even the weather control systems, how the monsoons will travel and how it will cover the entire country, the movement of monsoon or weather systems in general. These are based on mathematical models on weather systems, and based on that, they provide us the long-term predictions and short-term predictions. You must have observed these weather prediction systems. Even in military applications, these mathematical modeling concepts are utilized. Briefly, we saw in the last class how this control system analysis tools can help us in assessing the performance of a given system. Now, to come back to our curriculum as such, these two units, as I said yesterday, we are going to cover. And though it is a branch in itself, it's a vast field of knowledge of control systems analysis. We'll try to make justice to this topic of control systems engineering, even though some topics are not covered in the syllabus. We'll try to include those so that there'll be an understanding of the concepts of control systems engineering and its applicability in various fields of engineering. Talking about our curriculum, we are going to study some of the aspects of open loop systems, closed loop systems, some aspects of representation systems like block diagram algebra. We'll be studying some aspects of mathematical modeling of mechanical systems as such. And then we are going to study some of the controllers related to control systems, which is of course related with mechatronic systems. Then we are going to study the stability aspects of control systems, and finally we are going to see some of the frequency response techniques like Bode plots and brief introduction of state space techniques as such. Though this syllabus is randomly distributed, I'll try to streamline it so that there'll be a definite flow in the body of understanding of control systems engineering as such. As discussed yesterday, I told you the case of design of hydraulic turbine for specific applications. I also told you about development of a robotic device as such. For that matter, whatever system, new system I'm going to design, I need to carry out in-depth analysis either by using softwares as we mechanical engineers do, by using ANSYS, and there are by using ANSYS we carry out strength analysis of various components. By making use of some softwares related to dynamic analysis. You have ADAMS as one of the dynamic analysis softwares. I can virtually develop a mechanism and I can predict the performance of that mechanism. I can find out what would be the velocities and accelerations of various elements and what would be the inertia effects of those components. So likewise, by making use of softwares, I can, by using some solid modeling softwares, I can build a virtual model, 3D model. I can animate it. I can apply certain boundary conditions, apply certain forces, apply certain constraints to the motion, and then by giving variety of inputs, I can just visualize how would be the motions transmitted, how would be the force transmitted, how much will be the stresses induced, and what would be the fail-safe limit of the component. This is one aspect of modeling and analysis of mechanical systems. The second aspect is performance evaluation of a given mechanical system, so to say. If I take the case of maybe a suspension system of an automobile, what I do is I define the requirement of suspension system, maybe a two-wheeler suspension system I'm going to design for that matter, let us say. So if you take the case of a two-wheeler, there'll be a rider of a two-wheeler and there'll be the pillion, the man sitting behind the rider. And then you have the vehicle mass, then you have the front suspension system and rear suspension system. Then we have the drive system, we have engine system, and then we have the controls for operation of that motorcycle. So like that, there can be electrical systems, there can be power generation systems, so to say. So for this two-wheeler, if I'm given a task of developing a suspension system, so what will happen? Just try to visualize a two-wheeler, any motorcycle for that matter. It will be carrying its own weight, its own mass, let us say, and we have to consider the masses of the rider and the pillion rider. So the total mass will be distributed amongst front wheel and rear wheel. Let us assume it to be equally distributed. So whatever is the mass, total mass, that will be distributed on front wheel and rear wheel. So let us take the case of a rear wheel suspension system design. So half of the mass of the total mass will be borne by the rear wheel suspension system. Now what is there in the suspension system? Let us say we have two shock absorbers. Now if you look at the shock absorber, what will be there? The spring that is visible. So spring having specified stiffness that is visible. So that spring, and then you have a damper which absorbs the shock. So you have, so to say, a mass, spring, and a damper, right? So we have specifically some mass, we have specifically one spring, and we have specifically one damper, right, which does the work of shock absorption. So these are the basic elements of my suspension system in a given example. It will be having certain mass, it will be having some spring of certain stiffness, and then it will have a damper having certain damping coefficient. Apart from this, if you just try to be more practical, the drive that is given through the rear axle, through the wheels, through the spokes, to the rim, then I have a tube and tire. And the tire and the tube has got certain elastic properties. So this tire and tube, they have elastic properties. So those are also my stiffness-like elements, my spring-like elements, because they behave like a spring, isn't it? So I have a tire and tube acting as additional stiffness elements. So basically what we had, mass, then one stiffness, that is spring, having certain stiffness, then I had one damper, having some damping coefficient. Some fluid is there inside that damper, and provides me the cushioning effect, right? So apart from these elements, I have stiffness like elements like tire and tube. Then I have the inflated tube, that is air is there inside the tubes. What work they do? They provide me the cushioning effect, isn't it? That air provides me the cushioning effect. When it is subjected to impulsive forces, it will just get compressed and it provides me the cushioning effect. So that air will act as a damping element, a damper-like element, right? So, and apart from this, you're sitting on a seat. Now, seat has got certain springs, it has got certain sponge, that cushion is there. So, to make our ride comfortable. So, inside the seat also, I have got stiffness elements in the form of springs. Then I have the cushion, which provides me damping like elements. So, all these stiffness like elements, I will combine and represent it in the form of a spring. Spring does not necessarily mean only spring. The components or elements which are behaving like spring. So spring and spring-like elements will be represented by one spring. Then mass and mass-like elements. What are the mass-like elements? Mass is the mass of the structure of the two-wheeler, isn't it? Whatever frame I have got, whatever uh, mass of each component. Then I have mass-like element, the rider and the pillion rider. So they are mass-like elements. Plus, I'll be putting some load. काहीतरी मी मागे एक bag ठेवली आहे. It has certain mass, isn't it? So that is also mass-like element. So clubbing all these mass-like elements together, I show it in the form of a box, and I write mass M. Right? I'm talking to you about how we represent a free body diagram of this suspension system. We are into now control system. We are trying to represent that physical system in the form of a block diagram or in the form of a model. Okay, a representational model. So I have mass block, then I have got spring. I can draw one spring. What would it would include? The spring proper used in my suspension system, plus the spring-like elements having certain stiffness. So equivalent stiffness K, I'll be considering, I'll be showing one spring. And then I have a damper. Damper is damper proper, which is used in a shock absorber. That is the damper having certain damping coefficient. Plus, what are the damper-like elements we discussed? The air, inflated air in the tube, that also does the work of damper-like work. Then I have got the cushion, sponge you provide. There will be air inside that sponge also. So that provides me the cushioning effect. So those are the damper-like elements. Then we have the tire tube, which are spring-like elements. So what I do, that physical structure of a suspension system, instead of drawing it fully, what I do, I prepare a simple line diagram in the form of, I show one mass M, equivalent mass, and then I show one spring having some stiffness K, and one damper I show in the form of, let us say, having some damping coefficient C or B. We can name it anyway. So, and then these are connected to the ground because this is resting on the ground. It is moving on the ground, isn't it? So this will be my representation of that suspension system. So what is the use? I can understand the functioning of this suspension system. Now one would ask, what will be the use of building such a model? As we discussed in the last class, what I do, I told you about showing mass, showing stiffness K, showing damping coefficient B or C. I have represented that model. Then I show the forces, how external force is acting. What we'll take the actual case. Now this tire is moving on a bumpy road, let us say. So because of that bumpy road or a ditch or a speed breaker, whatever is the disturbance, what will happen? This tire and the vehicle will be subjected to some external disturbing force. So I can show that force F acting on this spring mass dashboard system. I can show F, right? And then because of this F, what will happen to the vehicle? We all will be sprung up, isn't it? Including the rider and the pillion rider, the entire vehicle will be pushed up. Without a suspension system, it will be pushed up higher, depending on the height of the bump or the speed breaker, or depending on the qualities of my damping system, the stiffness values and damping coefficient values. This springing up, this will be pushing up, this is bumpiness will be reduced. That is what is the function of my suspension system. So because of this force F, what will happen? There will be displacement X of the mass, the spring, and the damper. Isn't it? So I show it in the form of, let us say, X. So on my model of spring mass dashpot system, I show the external acting force F, and I show the displacement X. Isn't it? So what I've done to my block model or functional block diagram, I have added the parameters, the force parameter and displacement parameter. And let us say we are going to study this in details just to tell you what is the utility of this analysis. So let us say it gives me one equation. Now, what will be the governing equation of this spring mass dashpot system? It would be based on maybe Newton's second law. What Newton's second law says? Summation of all external forces. Summation of all the external forces will be equal to mass into acceleration. That is, F is equal to ma. Isn't it? Summation of all the external forces will be equal to mass into acceleration. F is equal to ma, the equation that we know based on Newton's second law. What are the external forces now? The external force I am applying is F. And because of this external force F, what will happen? The mass will be displaced, the mass will be accelerated even, and then the spring will be displaced by amount X, the damper will be displaced by amount X, or it will be moved by velocity Tx or V, whatever it is. So because of this external force F, I am getting displacement X, velocity V or velocity dx by dt, and acceleration d2x by dt square, right? So the external force is F. Because of this force, the spring will be displaced. Now, once the spring is displaced, what will happen? The spring force would react. The spring would react. Let us say, we'll study this in detail just to give you an example. It is the spring force is equal to K into X. And the damping force is equal to, let us say, the damping coefficient is C into velocity. Now the force, damping force is proportional to velocity. Spring force is proportional to displacement. So what I ultimately get is all the summation of all external forces, applied force F, let us say, and then I've got the spring force Kx, and damping force is equal to C into V, or let us convert C into V as C into dx by dt. Now dx by dt can be converted into operator form by using, what is operator D? Operator D is nothing but d by dt. So velocity will be represented by V is equal to C into dx by dt, or capital D into x. What this capital D into x means? Dx by dt. Okay. So the velocity will be represented by dx, capital D, small x. Dx corresponds to dx by dt, and this dx by dt is nothing but velocity. So damping force is proportional to velocity, and ultimately, let us say I get one mathematical equation of operation of this simple suspension system. As how we are going to do it, we'll do it in the coming classes when we study the mathematical model. Let us say I get one equation as external force F is equal to the mass will be displaced m into a, as I said, isn't it? I have force is equal to m into a. Summation of all F is equal to m into a. Now this a is nothing but d2x by dt square. Now converting into operator form, what it will be? d2x by dt square will be equal to capital D square into x, isn't it? Capital D corresponds to d by dt. D square corresponds to d2 by dt square, isn't it? So I have dx d2x by dt square, isn't it? So that is velocity. So I have summation of all f equal to mass into d2x or d square x. So md square x. And let us say ultimately I get one equation as external force F is equal to md squared plus cd plus k entire bracket multiplied by x. Now what is this? F is equal to md square x, which corresponds to, what is this md square x corresponding to? M into a, md square x plus cdx. What is the cdx? This is the damping force. C into dx, c into dx by dt, cdx plus kx. What is this kx? Kx is my spring force, isn't it? So it is summation of all the forces. So external force F is equal to, or summation of all external acting forces is equal to internally reacting forces. Can be one form of equation representation. So what I have got? F is equal to md square plus cd plus k entire bracket multiplied by x. Okay, we'll separate out. Now, just try to take a piece of paper and write down F is equal to capital M d squared plus C capital D plus K bracket multiplied by X. Okay, so what is the input now? Input is external force F, and what is the output? I am getting X. So let us convert this equation into output by input form. What was the equation? F is equal to md square plus cd plus k bracket multiplied by x. X is my output and F is my input. So X by F is output by input. So X by F is my output by input. In control system terminology, this output by input ratio is called a transfer function of the spring mass dashpot system. So transfer function of the spring mass dashpot system is equal to output by input, which is equal to, what is the output in this case? X, and what is the input? F, which is equal to X by F is equal to 1 upon md squared plus cd plus k. So this is the transfer function I have obtained. Now what is the use of this transfer function? Now, as I discussed in the last class, I can see I have not designed, I have not manufactured any suspension system component. What I have done, I have just built a mathematical model for the performance of this suspension system. What I have got, the transfer function of this suspension system model is X by F. X is displacement X by F is equal to 1 upon md squared plus cd plus k. Now what is this? M corresponds to mass, C corresponds to damping factor, and K corresponds to stiffness. Now, by using this transfer function, I can predict how my suspension system is going to behave. I input, now this is actually the differential equation of operation. I have converted into transfer function form. What I do, I input some value of force F, some Newton. Now, corresponding to force F, how much would be the displacement X? By subjecting to a force of maybe 100 Newton on this vehicle, how much will be the displacement? Isn't it? We must have experienced many times in buses where the dampers are removed. You are just thrown up. The displacement transmitted is very high. Now, I can just find out mathematically how much would be the displacement transmitted, how much would be the force transmitted by using this simple transfer function. Okay, so whatever X I am predicting corresponding to F, I know this is going to be this X. Let us say corresponding to 100 Newton of force to this suspension system, I am getting displacement of 100 mm. Okay, now I want to reduce this displacement to make my ride comfortable. So we should not be thrown up, isn't it? Would like we lose the control of the vehicle, isn't it? So the displacement transmitted should be minimum. The force transmitted आपल्याला टोचायला पण नाही पाहिजे ना. दणका वाजला की you cannot sustain that impulse force because of the bump. खड्ड्यातनं गाडी गेली, कधी स्पीड ब्रेकरनं उडाली, आपण म्हणतो की नाही. त्यामुळे there is some force transmitted, there is some displacement transmitted. We want to reduce this force transmitted and displacement transmitted. How we can do that? This is where my transfer function will be coming to my help. We are working on paper, remember. As I told you, what is the example I took? 100 Newton I have applied, I am getting 100 mm. I want to reduce this displacement x to 50 millimeter. What I need to do? Come to the right hand side of the transfer function. 1 upon md squared plus cd plus k. Now let us say mass I cannot change. So I don't touch the term mass. I can change the damping coefficient c. I can change the stiffness K in such a way that I get x is equal to 50. So this is how I can subject this mathematical model to different input functions, and I can predict how would be the output. This is the beauty of this mathematical modeling. This is not just the case of a spring mass dashboard system, any system for that matter. Any motor system, any drive system, any hydraulic system, any pneumatic system, any satellite control system. Rather, this is what is done before a first prototype is built. A mathematical model is prepared, and that mathematical model is subjected to a variety of conditions. Just to share with you, the predicted path of my satellite or my rocket launcher, maybe on a moon, on Mars. All these predictions are done beforehand by ISRO and similar agencies, NASA. What they do, they prepare a mathematical model defining the dynamics of my rocket propulsion system, and they can exactly predict in how many days, in how many hours, what would be the location, how precisely we can do, because that mathematical model is so practically perfect that the predictions are matching. So let it be a surgical system, critical system, military system, I can make use of this mathematical modeling and predict the performance of my given system by using this. So in these 2 units in our curriculum, we'll try to understand few aspects, how to predict the performance of my system and how to predict the behavior of my system and how to modify a given system design to suit my requirements. This is what we are going to discuss. In the next class, we'll discuss few more aspects. Okay, the next teacher is waiting. So we'll stop for today.